I'm going to also jump forward in time here just a little bit. Because the last thing I played is still showing you the entire view as it is usually projected on the dome. So yeah, the Dome Theater here is a 1/4 acre screen, 76 feet, about 23 meters in diameter. Largest screen in the state, worth a visit when you get a chance, and it is safe to do so. They can do pretty cool stuff. We use special software designed for theaters like that called Digistar. I'm using Digistar 7 for today's show. But because we're stuck on these small flat screens, I will not make you try to also interpret the round video as we go here. So I will switch to the rectangular view for you. So maybe that looks more like a regular video. You can kind of make some sense of it. There is the museum. That is what you're looking at there. The entrance that you would come in. Let's see, I don't think you'll be able to see my mouse cursor, but probably see this giant floating red hand. The main entrance would be right here. The big pendulum, Foucault pendulum, is under this dome that is over our main lobby. You come down the hallway. The Planetarium Theater is under that white colored dome. So that is where the show makes the most sense, but we'll see what we can do on a flat screen for you as well. So if you were to go outside later on tonight and look up at the night sky, well, you're not going to see a whole lot tonight. I believe the forecast is for it to stay pretty cloudy. I think it is raining right now. I've not been out of the basement all day, so I'm not sure what's going on out there. But if the internet is to be believed, it's not a great night for looking at the stars. But I can still show you what is going on out there. Here is the situation. One big thing that I want to show you tonight, if you were to go outside, face south, you would find one pretty bright star, the brightest star in the whole sky, and then not too far away, a pretty famous constellation, the constellation Orion. You can recognize Orion because of the 3 stars in a nice straight line. I've got it more or less centered on your screen here, and as long as I don't make any typos, I can put a little outline of the constellation up there as well. Now, I show you this not really to talk about the stars or Orion itself, but because Orion is a useful guide in the nighttime sky. If you can find those 3 stars in a line, you can trace out the rest of the shape of the constellation. You can use it to point you towards all kinds of other interesting things. And I just want to show you one tonight. In the interest of time, I will not show you the entire nighttime sky, especially because I've got to do so much reorienting and spinning around on this little screen that it would take all evening. So all I really want to show you is that if you use those 3 stars, you can imagine drawing a line between them, and if you stretch it up and to the right, you're going to pass a couple of interesting things. It'll go right by a bright kind of reddish star named Aldebaran. It'll take you through a little cluster of stars, the Pleiades, but about halfway between those is the planet Mars. And let me see if I can get that marked for you here too. You can recognize planets in the nighttime sky relatively easily because they tend to be a little bit brighter than the stars around them. You also notice they don't twinkle like the stars do in the nighttime sky. And then with the help of Orion, these days, you can get yourself pointed right towards Mars in the sky. I wanted to bring that up because, of course, the planet has been in the news a little bit recently. We sent spacecraft to explore Mars from time to time, and Mars just received a couple of new visitors. So let's go check in on that planet. Now, right now at Mars, there are 8 spacecraft in orbit and 3 down on the surface. But 3 of them are newcomers from that whole fleet. 2 brand new orbiters arrived early in February. One was launched by China, the other launched by the United Arab Emirates. The 3rd new spacecraft to arrive at Mars this year is NASA's latest rover, the Perseverance rover. It sat down safely on February 18th, so almost exactly a month ago. The region that it landed in is what you're seeing now. This is called the Jezero crater, or if you watch NASA coverage, Jezero crater is what they use a lot, going with the American pronunciation. And there is the location of the rover. Now, a few things I can show you here. I can let you know that to get safely to the surface of the planet, the rover needed to use a parachute, a heat shield, a little rocket backpack. We know where all those landed on the surface too. But the rover itself, of course, is the most important part. In the last month, it has been driving across the surface, off to a kind of slow start. As you can see there, has only covered about 6/100ths of a mile across the surface of Mars, right around 100 meters so far. But you know, every mission starts with a few small steps. So here is the location of the rover. So far, it has been occupied with testing out its instruments, making sure that everything survived the 7-month cruise to Mars. It has taken some pretty good pictures. I've got a nice high-resolution panorama. It's got a mast that sticks up off the top of the rover to actually sort of simulate what a human would be able to see on Mars. Its cameras sit a couple of meters, about 6 feet off of the surface of the planet. There are 2 of them, so you get stereo vision, just like human eyes give you. So something like what humans would see on Mars, though wouldn't be wrapped around a planetarium dome. So you wouldn't have this curvature if you were actually there. But the resolution of the cameras is pretty good. Zooming in on a random set of rocks sitting in the area where the engines kind of scoured away some of the dust. And once they get the software all updated, you'll actually be able to see about 3 times higher resolution. So pretty good stuff to come from those cameras. Let's see, a couple questions coming in. China, what other country launched spacecraft to Mars? Yeah, United Arab Emirates was the other one. China's Tianwen-1 spacecraft, the UAE's Hope mission, and then Perseverance, they all launched last July. They all arrived at Mars in February. Those first 2, Tianwen and Hope, are just orbiters. The Chinese mission does have a lander along with it that is expected to try and land in either May or June. So I've got to wait for that landing. As for Perseverance here, it is going to continue on exploring Jezero crater here. Its main goal is to get over to this rock formation over here. If you're familiar with maybe a little more terrestrial geology, what goes on here on Earth, this looks a lot like a river delta. And we think that's what it is. It looks like some water must have broken through the wall of the crater over here. As it filled, the crater would have dropped off some of the sediment that was carrying with it, built up this alluvial fan here, built up a little river delta. And there may have been a lake in this region for a long period of time. Obviously, no water here today. Perseverance is a rover, not a boat. But we think that there was water here for a fairly long period of time. And other missions have shown that maybe the chemistry was right on the surface of Mars to at least not be hostile to life. So Perseverance is really trying to drill down and see if this region was ever hospitable to life and whether life ever developed. So it's got instruments on board to look for signs of organic chemistry actually caused by organisms. That'll be able to search for microscopic fossils. It's also going to be collecting samples that, if all goes according to plan, will be retrieved by future missions and returned to Earth in a couple decades. So a little time for all that to work out, but it'll be able to analyze the samples select the most promising samples, store them in little vials, and they'll be left behind for another rover to pick up later. If none of that interests you, the rover also has a little hitchhiker. There is a drone strapped to its belly right now. It's a little rotorcraft. The plan of the next couple of weeks is to drop this helicopter off. Then it will attempt flight. It'll be the first aircraft to fly on another planet if everything goes well. So there you go. New missions at Mars, active exploration of the solar system. Wanted to share that with you since that's going on right now. Other topics that I wanted to cover, though, let's head back home. So we got Mars in the nighttime sky. Already mentioned that the weather is probably going to prevent you from finding it in the sky tonight. So maybe you have to go out another time to see Mars. Thing is, if you don't go out 2 hours after the sun sets tonight, Mars will not be in exactly the same position. I'm showing it to you here, high in the southwest. So how must you find Mars at another time? Well, to help with that, let's take a look at how things change in the sky as we move through time. The first important thing to note is that Earth is always moving. It's moving in a couple of ways. Earth is rotating around its axis, spins once every day. That's what gives us sunrise and sunset, makes the sun appear to move across the sky. It makes the stars appear to move across the sky as well. So if it were clear tonight, if you went out right after sunset, Mars is in the southwest. If you go out a little bit later, it will have shifted though. Things in most of the sky appear to move from east to west. So here, if I point us back down towards the horizon here, I'm just running us through time. Accelerated it just a little bit. So the stars are moving across the sky. That's pretty neat. But if we point to the north, we can see the stars do a little bit different dance over there. Let's see if I can not crash us into the earth here. There we go. There's north, try and get it to stop, and time should start moving for us again here in just a second. Now, up here in the northern part of the sky, some of the stars move in a little bit different way, and since they might be kind of hard to see on your screen, I'm going to try and make it slightly easier by making them leave trails as they move. So up here in the northern part of the sky, things are sort of moving in giant circles. And that is because the Earth's pole is, well, where it points in the sky, it's visible in the sky. And that actually helps us define a coordinate system that we use in space. I think you've usually talked about it in your classes or your labs by this point in the semester, so you might be familiar with it. You will see or have seen celestial globes, celestial spheres. We've got the Earth in the middle, then a transparent globe around it that gives you a sense of these coordinates. And I'll try and show them to you on the screen as well. So let's jump up off the surface of the Earth, see what these coordinates really mean. So there's where the pole points. Let's see the Earth for a second. These celestial coordinates are closely related to coordinates we use here on the surface of the Earth. The Earth has two poles, of course, a north and south pole. I'm going to mark those for you. It has an equator as well. So one way you can think about the celestial coordinates are just an extension of the more familiar latitude and longitude system we use here on the Earth. The celestial poles sit directly above Earth's poles, its geographic poles. So the north celestial pole is over the north pole of the Earth. The south celestial pole is over the south pole of the Earth. And then there is a celestial equator shown to you in yellow here on the screen. And you can think of that as being situated in the sky directly above Earth's equator. That then means that just like every point on Earth can be defined by a pair of numbers, a latitude and a longitude, every point in the sky can be defined by a pair of numbers as well, or at least a pair of coordinates. Astronomers, never wanting to make things easy on people, have defined these numbers in slightly different ways. Instead of just something like latitude and longitude, a degree system, astronomers invented something called right ascension and declination. Some of this is related back to the measurement of time and how that's been related to astronomy over history. But right ascension is measured in usually hours, minutes, and seconds. So the sky is split up into 24 hours of right ascension. Then declination, that's just degrees, because why would it be anything else? So everything in the sky has its own pair of coordinates, so its own right ascension and declination. Let's see if I can find the North Celestial Pole, get it on the screen for you again. And as luck would have it, the numbers are also more or less upright here. So the North Celestial Pole is well, its right ascension is about 2.5 hours. But the important thing here is that it is so that's the location of Polaris. It's not exactly the pole. That would be exactly 90 degrees in declination. So that's the North Star. That is almost exactly at 90 degrees declination. It sits almost directly above the Earth's North Pole. I marked a few other things of varying interest. I think somewhere on the screen, if I rotate in the right direction, we can find the coordinates of the center of the galaxy. I've got the coordinates for, I believe, the Andromeda galaxy are on here somewhere. But I could have labeled any star I wanted on the screen. They all have their own unique coordinates, and that's pretty important to know. The stars appear to stay more or less fixed in their place in the sky, unless you plan to live for thousands of years. But there are things that appear to move among the stars. You can't really see them move from night to night, but you can see them move if you watch the sky from night to night, week to week, month to month. And Sydney has asked, can you see all the planets in our solar system, even dwarf planets such as Pluto? Well, if you've got telescopes and you know where to look, sure, you can find them in the sky as well. And these coordinates are going to be pretty useful for that. I don't know if I can turn them all individually, so let's check some of my controls here and see if I can get the coordinates for a few planets on there. I think these are going to be really, really small on your screen, but I'll turn as many on as I have quick access to here as they slowly page in, and I don't even have it set up to give you the coordinates. But yeah, you can locate the planets this way. If you don't have fancy equipment, your best bet is just look for the planets out to Saturn. You can see those naked eye without binoculars, telescopes, anything like that. Good rules of thumb for finding those planets: look for the brightest things in the sky. The planets are usually brighter than the stars around them. It's not a perfect rule, but it's good 9 times out of 10. And then watch for the things that don't twinkle, and that's what really gives the planets away. Things farther away than Saturn, Uranus, Neptune, Pluto, other small things, Pluto and the dwarf planets. You need telescopes to help you locate those, but they are all out there. And if you really pay attention to the sky, you'll also notice that those objects are out there because, well, they shift relative to the stars in the sky. So let's see if we can get a demonstration of that going. So conveniently, Mars was in the sky this evening. So let's jump back to tonight. Jump back to the skies above the museum here. It'll look nice and high in the southern part of the sky. So Orion back down at the bottom of your screen. Flash that constellation up there for you for just a second. Okay, so there's Orion. Got your bearings there. Hopefully Mars off to the right. But that's just tonight. And as I've already mentioned, the sky is going to be too cloudy to pick this up in the sky tonight. So what if you try another night? Well, And if you got it exactly the same time as I am showing you here, which I believe is about 8:30, 8:45. Say you try 8:45 tomorrow. Well, here's the position of the stars, 8:45 tonight. This is a much better illustration in a dome, but bear with me. The exact same time tomorrow night, that's where the stars are going to be instead. Maybe you didn't see much change. So I'm going to shift through a few days here, and I'll tell you what, we'll just make it a little time lapse here. So I'm just jumping forward one day at a time, and on those time scales, the stars don't appear to move relative to each other. To make this work, I'm also locking our vision onto one set of stars. So now even the sun has appeared on the screen. But over long periods of time, you might notice that these bright objects that don't twinkle in the nighttime sky are moving relative to the stars in the sky. And that was really the giveaway for ancient peoples around the world, that these objects were just a little bit different. Because people thousands of years didn't have telescopes, they counted 7 planets in the sky, what we today call the sun and the moon, and then Mercury, Venus, Mars, Jupiter, and Saturn. You could trace their motions across the sky, and so those objects seemed pretty special. We now know those are just the other objects here in our solar system. The sun, we now know, is at the center of the solar system. But for us, as we look up at the night sky, we still see those 7 more familiar objects moving against the background stars. If you follow them carefully, as you may be noticing here on the screen, they'll kind of move across the same part of the sky all the time. So the naked eye planets, the sun and the moon, are all moving across the screen here. They're leaving trails behind them. They're all staying pretty close to a line that is kind of stretching from the top left corner to the middle of the right side of the screen, or I guess so they go the other way across the sky. Switch that around. That line is called the ecliptic, and it's another important reference point in the sky and in astronomy. It is not the same as, say, the celestial equator. These 2 lines are actually at angles because, well, this line is well, it's really just an extension of the Earth's orbit across the sky. So let's jump up above the solar system here, bring the orbits of the planets back, and still got the ecliptic on the screen in the background, but it's just kind of blending in with the orbits of the planets, because that's really what the ecliptic is marking. It's an extension of the Earth's orbit across the sky. Or technically, it's the sun's apparent path across the sky, but those are really the same thing. So that ecliptic marks where the planets can be found in the nighttime sky. That brings up another interesting point. In just a couple of days, we're going to mark the equinox, the March equinox. For us in the Northern Hemisphere, it is the technical beginning of spring. Why does that happen? Well, it's the difference between the ecliptic in the sky and that celestial coordinate system, or if you drill down to it, it's the difference between the angle of the Earth's axis, its obliquity, and its orbit around the sun. Let me try and show that to you in a couple of ways. First, kind of, I don't know, this is more the classic way to illustrate this. We've got the Earth in orbit around the sun here. I'm going to try and make it a little bit easier to see on the screen here. So I've made the Earth a little bit bigger than it actually is compared to the sun. And as I go through one year, I'm just making little copies of the Earth so we can sort of try to get a handle on the situations. If you look carefully, I've marked the poles of the planet. You see these 4 important points. They turn out to be the 2 solstices and the 2 equinoxes. And if you look carefully, the amount of sunlight that especially the North Pole was getting changed a lot at those 4 points. Now, another way to illustrate this is to change our reference frame just a little bit. We're going to lock on to the planet Earth. I'm going to get rid of everything in the background because, well, I'm going to cheat here just a little bit. I'm going to keep the sun locked to the left-hand side of the screen here. And so in reality, as I move through time, the stars are moving wildly in the background. We're going all the way around the sun once every few seconds. And here it looks like the Earth is wobbling on its axis, but that's probably not the best way to illustrate it. So let me erase this view from the screen, and instead let's go back to those coordinate systems. So let's join the Earth in space here, bring the stars and all the other background objects back. Let's see, I believe this will add the equator and the poles to the Earth again. We're going to stretch those out again. We're going to put the celestial coordinates back on the screen. But this time, I'm also going to add the ecliptic to the screen at the same time, so that you can truly see that these coordinate systems are a little bit different. So I'll try and get the sun on the screen here as well. There we go. There's the Earth's orbit. So blue line is the Earth orbit for the ecliptic, if you'd like. And then off in the background, I've got the sun. And what is going to happen here in just a few days is that, well, the sun, as we see it from here on the Earth, is going to cross the celestial equator. So time is running here. You might sort of be able to see it, but let's speed things up here just a little bit, though. Getting pretty close. Here in March, the sun moves from the south celestial hemisphere to the north celestial hemisphere. What that means for us here on the Earth is that, well, every day in the northern hemisphere, the sun is going to start climbing higher and higher in the sky. At midday, it's going to rise and set a little bit farther north as well. If we were to reverse time here and try and get back to the winter, well, the sun would be in the southern half of the celestial sphere, and it would be much lower in our sky. I'm going to prove that to you by heading to the surface of the Earth. For this, I am going to restore that round view because it does do a nice job of showing us the entire sky as we see it. So little tiny red letters are showing you the four cardinal directions. So south is at the bottom of the screen, north is at the top, east, left, west to the right. And if we just speed through a couple of days here with the clouds, it's a little bit easier to see. In summer, the sun rises and sets at fairly extreme points to the north of east and west. In the summer, with the solstice, it rises farthest north and stays its lowest in the sky at midday. What we're going to see on the equinox is that it rises more or less exactly in the east and west, and it reaches kind of a middle point at midday. It gets the name equinox because the duration of daylight and darkness at night roughly equal on that day. So sunrise, sunset, roughly 12 hours apart. So you get roughly 12 hours of darkness in between. And it's also a day when you get about that same 12 hours of daylight and darkness on every point on the Earth. So, so in another sense, we kind of share that that moment with everyone else on the planet. So, I think that's kind of a neat way to look at it as well. So there you go, the equinox, changing of the seasons coming up. Let's see. Then let's transition back to this nice view so that we can talk about other things out there. If the computer will keep up with me. All right, so there's our rectangular view again, yeah, let's talk about the rest of the solar system. Since you asked about dwarf planets and Pluto, let's see what's out there. So I am going to need to, let's see, jump up off the surface of the planet here. That's the most important part. If you want to see the rest of the solar system, and let's put some objects on the screen for you. So let's. Ooh, I know a great way to do this. Let's sort of drift away from the Earth, and let's have the computer fill in our map of the solar system as we go. There is the Earth. That's where we are now. Probably recognize it from the maps. Now, if we drift away from the Earth, the first thing that we should find is the Moon. It's our closest neighbor in the solar system, only about 250,000 miles away from the Earth, to make it a little bit easier to pick out because it's fairly small. I've added its orbit to the screen there, so you can see the path that the Moon takes around the Earth. That's the farthest that people have gone in the real universe. We send robots a lot farther, and it's allowed us to explore and map the other planets in the solar system. That blue line you're seeing is the Earth's orbit around the Sun, and as we drift away here, the orbits of the other inner planets will appear as well. So we've got the Sun at the center of the solar system, then Mercury, Venus, Earth, and Mars in orbits around it. Just beyond the orbit of Mars, we've got a few more objects. That is the main asteroid belt. We've located in the neighborhood of 1 million objects in that region of space. The largest object in the asteroid belt is the dwarf planet Ceres. You're seeing that orbit there as well. Then beyond the asteroid belt, we've got the gas giants in the solar system, orbits being shown here: Jupiter, Saturn, Uranus, and Neptune. And then beyond Neptune, just a few other objects in the solar system. This is where Pluto orbits the Sun. This is where most of the other dwarf planets are located, along with a few thousand other worlds that we have been able to discover out here. Probably thousands more, maybe millions, but out here, these objects, well, nothing but the Sun emits light of its own here in the solar system. So we have to rely on reflected sunlight. And because these objects are pretty far away, over 3 billion miles away from the Sun, or if you prefer astronomical units, a little over 30 astronomical units, and they're fairly small. They're just really faint in the sky, so you need pretty big telescopes to see these objects, and so the real small ones, more or less invisible to us here on the Earth. And I should be able to expand our view here to the brand new record holder for the most distant visible object in the solar system. Let's see how this one works. Very nice. So this newest orbit on the screen belongs to a fairly small object. Astronomers estimate it is something like 250 miles or 400 kilometers in diameter or so. It is also a little over 132 astronomical units from the Sun, 11, 12 billion miles, something like that. It is the most distant object that we can see in the solar system. It's large enough that even though it is very far away, it reflects just enough light for the largest telescopes on Earth to see it. Now, that's just the farthest we can see. There are more objects out there, few thousand million, maybe billions of additional objects much farther from the Sun. We haven't observed any of them out here, but thanks to the occasional visitor to the inner solar system, we think that a lot of comets originate out here in a region called the Oort cloud that would really mark kind of the limit of the solar system. Amber asks, the farthest object we can see, does it have a name? Well, not really a name yet. Astronomers, of course, they've got code names and designations for everything. Officially, that object is known as, gotta get the right one here, it's 2018 AG37. That's a license plate number, lets astronomers know exactly when it was discovered. But the team of astronomers that found it, they gave it a little nickname because, let's be honest, 2018 AG37 doesn't just roll off the tongue. So they have nicknamed this one Far, Far Out. Of course, there's a reason for that. It's far, far out. But the same team also discovered another object about the same time. They announced it a couple of years ago. It was a little closer to the sun, and they named that one Far Out. So yeah, Far Out was the previous record holder. Now we have Far, Far Out. It will eventually, I imagine, get an official name, but there's a long list of rules the astronomers have to follow to make that happen. So it can take years for that to happen. So for now, Far, Far Out is a good thing to call it, or 2018 AG 37. So you go, there is the whole solar system, at least the major objects in the solar system. I left out a few asteroids, a few comets, a few moons as well, a couple hundred moons around planets and dwarf planets and asteroids in the solar system. So let's see what else is out there. Well, beyond the solar system, we should probably talk about the galaxy just a little bit as well. And well, it's kind of a fun story to tell. So it took us a little while to figure out our location in the solar system, convince everybody the sun was at the center of it. But how about the galaxy itself? The Milky Way is the name we've given to the galaxy we live in. You can well see every star that is on the screen. That's part of the Milky Way, and kind of faintly in the background here, might be able to see a fuzzy band of light. And I'll cheat once again, just a little bit, make that a little more obvious to you. So that fuzzy band of light is what most people think of when they think of the Milky Way. That's really our view of the galaxy from the inside. Our solar system, the sun, has some position inside the Milky Way, but where are we? Well, there are a few ways to try and answer that question. One thing you could do is just count the stars in every possible direction, and you would pretty quickly arrive at most likely an incorrect answer, at least with the technology most of us have available to us. That confused astronomers for a few centuries as well. They didn't have great luck counting stars in the sky. So what might work with a little bit better is to, let's see, remove some commands from the script that don't work in this version of software. And then perhaps abandon this path altogether and show you another method. I was going to show you, let's see, might be a way to do it. Astronomers, instead of counting stars, yeah, here we go, here's an alternate path. They started counting little clusters of stars. They're called globular clusters, and they're the slightly brighter patches that are on your screen. I'm going to make them a little bit brighter for you. And they noticed, looking around, that these bright groups of stars, these bright clusters, were not evenly distributed across the sky. We happen to be pointed to the location where they were most common to start with, but if we look off in some other direction, there aren't as many of them. So astronomers decided that, well, maybe these bright clusters of stars were evenly distributed around the galaxy, but because they are not evenly distributed across our sky, they can instead point us to the center of the galaxy and help us figure out the structure of our home in the universe. So studying a little bit further, it allowed them to work out that, yeah, if those objects are evenly distributed around the center of the Milky Way, then the sun itself is something like halfway out from the center of the Milky Way. You can map other things like huge clouds of dust and gas that helped astronomers figure out that there were well, some arms that seemed to be wrapping around this this central point of the galaxy. We can't see all the way around the Milky Way, but extrapolating from what we can see, we think the Milky Way has this kind of overall spiral structure. So believe it or not, astronomers have named this a QR. No, they named it a spiral galaxy. Some names in astronomy make a little bit of a sense. And we think that the Milky Way is maybe a little over 100,000 light years from side to side. Not the largest galaxy that we know of, but not the smallest either. Nice middle-sized galaxy, perhaps typical of other spiral galaxies that we see in the nighttime sky. Let's see, Alina asked, no one has traveled outside of the solar system, correct? Yes, that is very much correct. The solar system is a big place, and the speeds we can travel are relatively slow. We do have spacecraft that are, well, they're kind of getting to some extreme distances. Should be able to add those seamlessly to the screen here. Let's see, let's dive back into the solar system. And there's far out. There's the Kuiper Belt again. The most distant spacecraft we have, no people on board, just some robots, launched in the 70s. The Voyager and Pioneer spacecraft. Let's see what version of the script plays here. Tiny little labels that you probably cannot read on your screen. But on the left, there's a little dot that says Pioneer 10 next to it. On the right, going left to right, there are little dots that read New Horizons, Voyager 2, Pioneer 11, and Voyager 1. That order is just a little trick based on our current view. Both Voyager 1 and Voyager 2 farther than any of those others, and in fact farther away than far out. We know their locations because we're communicating with them with big radio antennas here on the Earth. So we know where they are, even though we can't see them. They are I guess the most distant tracked objects in the solar system. What's the farthest a person has traveled from Earth? Well, that'll be just a little beyond the moon. The Apollo 13 astronauts hold the record for the most distant point from the Earth, just because of the trajectory they took around the moon to return after the explosion on the spacecraft. They went a little farther away than all of the other Apollo astronauts. Off the top of my head, I don't remember exactly what the number is, but it's a couple thousand miles above the surface of the moon, I believe. So under 250,000 miles. So if we haven't left the solar system, not even with spacecraft, all this mapping of the location of stars and the galaxy, that's all done with other techniques. We can measure the locations and distances to stars in some cases. The most successful mission to measure the locations of stars is still ongoing. It is called the Gaia Spacecraft. And let's see, I think this will load a whole bunch of stars on the screen. It has maps now the location of about 1.7 billion with a B as in Baker, stars in the Milky Way, and that's given us distances to most of those stars, and that's really helped us fill in our map of our part of the galaxy. Though certainly our map is still incomplete, and the Gaia mission is ongoing, and there are a lot of other missions that are trying to map either a galaxy or other galaxies in other unique ways as as well. In fact, now that we've left the Milky Way, and before I totally wrap up the show, let's just put the whole universe on the screen for just a second. So we figured out our location in the Milky Way, not in the center, but not totally in the outskirts either. But a funny thing happens when we start mapping things farther away, because the universe is just so huge. Our map of it does kind of put us at the center. So that's the way it's going to look on the screen, but that's just a little bit of an accident because, well, we haven't had enough time, and the universe hasn't existed for enough time for us to see if it has an edge, or if we could ever map it all the way to its edge. So, yeah, the view is going to get a little bit strange here, but just know that a lot more to see here. So how do we know that this is what the universe looks like? Excellent question. Well, for these closer galaxies, and I don't want to get rid of the big blob in the center of the screen here. For these closer galaxies, we know what they look like because of big telescopes here on the Earth. And spacecraft, Hubble Space Telescope, and others have helped us map these nearer galaxies. So we sort of know what they look like. We know whether they are spiral galaxies like the Milky Way. Let's see if we can get sort of close to ones. We can see the spiral shape. So there's a couple of them. So a lot of galaxies out here are spiral shaped. And then there are other galaxies that, let's see if we can find one. They're big sort of elliptical balls of stars. So astronomers have called those elliptical galaxies. And those two big distinctions were picked up by the astronomer that the Hubble Space Telescope is named after, Edwin Hubble, about 100 years ago now. So the brighter yellow ones in this little cluster here, those would be examples of elliptical galaxies because they don't have those arms wrapping around them. And you see some spiral galaxies mixed in there too. Can we send probes to other galaxies? No, the distances are just too great. So the farthest we've been able to send spacecraft, the Voyager spacecraft, they're still here in the solar system. It's useful to measure their distances and the time it takes for light to get to them. So right now, the Voyager spacecraft are, off the top of my head, I want to say about 1 light day from the Earth. So if we want to send a command to them, send a radio signal towards the spacecraft, 24 hours later, give or take, that's just my best recollection of how far away they are, the spacecraft receives the signal. Now the nearest galaxy, its distance is not measured in light days, is measured in light years, and it's millions of light years, about 2.5 million light years to the nearest galaxy. So at the speeds that we can make spacecraft travel, there just hasn't been enough time in the history of the universe for spacecraft to travel that far. Even light is taking millions of years. So the way we see these other galaxies is, in truth, the way they appeared millions or billions of years ago. Do all galaxies contain something like the sun in the center? Well, the galaxies all contain stars. Every star is, every galaxy is a collection of stars, usually at least hundreds of billions of stars. But at the center of big galaxies, I think they're all built around supermassive black holes. We know there is a supermassive black hole at the center of the Milky Way. We know there are supermassive black holes at the center of other galaxies, and so we think that is typical of all the big galaxies in the universe. And speaking of all the galaxies in the universe, let's keep drifting away here. And this is where the view really starts to get kind of strange, like half the screen was dark a moment ago. So our mapping, as we get farther and farther away from the Milky Way, well, these galaxies are really far away. They're really faint. You need very big telescopes and/or very sensitive detectors to see them. So we've not mapped the location of every galaxy in the universe. And here in this view, the two big gaps on either side of the screen are because the dust and gas in the Milky Way get in the way and block our view. There are more galaxies than I can show you on the screen here, in part because we just can't see all of them, and even where we can see them, our mapping is just incomplete. So there's a lot more to see. But based on what we have mapped, astronomers are, well, still trying to nail down their estimates. A couple of years ago, the estimate was there could be a couple trillion galaxies in the observable universe. Now some astronomers say, let's dial it back a little bit. Let's keep it to a few hundred billion, but there's still a huge number of galaxies in the universe. There's even more I can show you, though. Let's back up a little bit farther. Eventually we will get to the edge of what we can see. It is called the cosmic background radiation, or the cosmic microwave background. Current thinking IDs it as the first light to travel through the universe. Right after the Big Bang, the universe was very hot and dense. Light actually couldn't travel through it. But at a certain point, a few 100,000 years into the existence of the universe, light could travel, and we still detect it today as a very cold radio emission. It's coming from all around us. So that's the kind of yellow and orange stuff you see at the very edge of the scene here. So I've got blue galaxies towards the center. Those are the ones that are sort of close to us, astronomically speaking. Yellow dots are even more distant galaxies, usually detected not in visible light, but in other wavelengths. And then we've got the cosmic background radiation at the edge of the observable universe. The edge of the observable universe, what we estimate, is some 93 billion light years away from us today. So that's really big. There may be trillions of galaxies out there. Each galaxy is maybe a few hundred billion stars. If the Milky Way is a good example, then each galaxy may contain twice as many planets as stars. So I've lost track of how many planets that could be. And Arena asked, do I think extraterrestrial life exists? And well, there are trillions of galaxies out there in the universe that life could have developed on. I think the number of chances, the statistics just say, yeah, there's extraterrestrial life out there somewhere. Is it nearby? Is it visiting us? Almost certainly not. But somewhere out there on some other planet, I mean, somewhere else in our galaxy, there's probably life. Maybe somewhere else in the solar system. If it's somewhere else in the solar system, it's probably microscopic, probably in an ocean under the icy crust of some moon. So we're not going to be talking to them anytime soon. But yeah, somewhere out there, I can almost guarantee that that life exists. Sydney asked, can you show us what other planets look like you did for Mars? Well, certainly the other planets in our solar system, that's no trouble. We have sent spacecraft to all the other planets at least once. So any particular requests, if I see a request or two come in the chat, we can fly to those planets in the solar system. But as we find planets around other stars, I can let you know that we know those planets are there, but we don't have good pictures of them, so we don't know what planets outside of our solar system look like. Jupiter or Venus. Sure. All right. So let's see. I believe all of this stuff will nicely disappear if we dive back into the solar system here. So let's try another planet. You listed Jupiter first, so let's do that. Ooh, I'm going to get rid of the Gaia stars. Let's see. All right. Ooh, Don't want to crash into the Earth, though. Don't try that at home. All right. So Jupiter. So got a little bit of clutter on the screen. Let me just clear some of that off. Let's see. We don't see the spacecraft anymore. We will get rid of far out as well. All right, and then sure. Other planets, those are easy. Jupiter. We can keep a pretty good eye on Jupiter because, well, it's the largest planet in the solar system. It's not terribly far away as planets go. It's only about what, half a billion miles, about 5 astronomical units, and it's large enough that telescopes here on the Earth can map its surface. Hubble Space Telescope is used to map its surface as well. So this view is a combination of images from the Hubble Space Telescope, as well as spacecraft that is here in orbit around Jupiter now, named Juno. I can in fact also show you that it's not just Jupiter here. Kind of like the Earth has a moon, Jupiter has moons of its own. And let's see, let's do this the fast way. And I guess some of the other planets' orbits are coming on for us here. But Jupiter has several moons. They're large enough to see in telescopes here on the Earth. So there are 4 big ones: Io, Europa, Ganymede, and Callisto. But altogether, Jupiter has 79 moons we have been able to identify and track so far. There may well be more, but kind of like it's tough to see things in the outer solar system because they are small and far away. Any moons of Jupiter that we have missed so far, they must also be pretty small, so pretty tough to see from the Earth. But since we've sent various spacecraft to fly by Jupiter, we've had what, 6, 7 spacecraft visit Jupiter now. We've got pretty good maps of some of the moons as well. So there's a little cameo appearance by Io also on the screen for you. It's the most volcanically active object in the solar system, but for just sheer number of volcanoes, it might be pretty tough to match Venus. So let's head there as well. And then we're getting down to the, we've already crossed the top of the hour, looks like, so should probably be wrapping up. But if there are any other quick questions, feel free to put those in the chat as well. And while we fly to Venus, I will look back to make sure there weren't other questions. Don't see any there. So Venus, let's see if we can get rotated around here. Venus, well, one little problem with showing you the surface of this planet. I got a combination of finicky controls on the computer, and well, Venus itself. It has a very thick atmosphere, and so that hides its surface from visible light cameras. So if you just send a spacecraft by Venus that has cameras that work like our eyes do, or if you point a telescope at Venus in the nighttime sky, you're not going to see a whole lot of detail. It looks more or less like this. But with special equipment, if you've got, say, a spacecraft that can well, use radar waves or radar to map its surface, you can peer through the clouds, see the surface of the planet, and I will eventually drill down through the controls here and peel those clouds away to show us a rocky planet, sort of like the Earth, but one that has just been totally reshaped by volcanoes. Most of the mountains and other features we see on the surface of Venus related to volcanic activity. Why Venus is so different from the Earth, even though it's about the same size as our planet, is still a little bit of of a mystery. And so a lot of planetary scientists want to go back to Venus to explore it in a little more detail. And in fact, there are 2 spacecraft that are finalists for funding from NASA, and perhaps one of them will be selected later on this year. So we'll send a new spaceship there, get some better views, because this map is what, 20, 30 years old now. So we need some better views of Venus. All right, didn't see any other questions come in, and given the time, I think that should probably end our exploration of the universe here. But hope that was interesting and useful to you. Hope that it maybe inspired some more questions, but you know, bring them to class next time, and have your instructors help you out with those.
Justin, maybe you can mention about your Facebook Lives. I know you're doing a lot of programs through Facebook, right? So maybe you can tell us a little bit about it.
Yeah, you bet. Every approximately 2 weeks now, we do a Facebook Live on Friday afternoons. So there's one coming up this week. It'll be Friday afternoon, 3:30 p.m. The show on Friday is going to get into some other topics related to time. So we flew through some big distances during this presentation, but of course, big time is an important thing in astronomy as well. So how do we know things in the solar system are billions of years old? How do we know that some stars are older than that? How do we know the universe is almost 14 billion years old? So we're going to cover some of that on Friday afternoon, starting at 3:30.
Yeah, so thank you so much for the nice presentation. And I wish really we were there in the planetarium, but anyway, it's really cool. Yeah, does anyone have any more questions or anything? All right, then. Thank you so much for joining. And I hope you get some chance to look at things a little differently than what we are doing in the real classes.
Thank you so much.
Thank you.
Super cool.
Hey, you're welcome. Thanks everyone for tuning in.